All right. So this is joint work with David Wang, Brian Williams, and Patrik Haslum. And so first, let me kind of remind you all what landmarks are in classical planning. So a landmark is a fact that has to be true at some point along every solution. So for example, to get back to Boston, I need to be at Ben Gurion Airport. There's no other way to get to Boston, unless you want to swim. So then there's the notion of an action landmark, which is an action that has to occur in every solution, right? So to get back to Boston, I have to go out the door. And then we can talk about disjunctions over facts and actions, right? So to get back to Boston, I have to take, let's say, flight A or flight B. And we can order these landmarks, right? So before I get to Ben Gurion Airport, I have to exit this room. And before I get on the flight, either one of these, I have to be at the airport. So that's what happens in classical planning. Now, in temporal planning, we can use the notion of landmarks from classical planning if we basically take each derivative action and break it into two snap actions, right, the start and end events. And we create basically a relaxation, right? So that's what Patrik did in 2009. And if we find the landmarks of this classical relaxation, then what we get are basically the causal landmarks, right? So these are the landmarks that are caused by the preconditions and effects. So now I want to describe an example temporal planning problem, and it's going to be a variant of the well-known match cellar one, okay? So our goal is to fix the fuse in the cellar, and there's two actions I can take. I can fix the fuse, which takes 10 seconds and requires light throughout. And I can light a match, which requires a match at the beginning. It provides light for 15 seconds and consumes the match. So that's the standard one, but we're also going to add a flashlight. Okay, and that flashlight is somewhere in the dark cellar. So before I can use the flashlight, I need to find it, right? So to find it, I need to have some light. And it takes me 2 seconds to find the flashlight, and then I can turn it on. That takes 1 second, and then it produces light until the end, okay? And so in my initial state, I have a match, and the fuse is not fixed. So we model this in a fairly straightforward way. The fixed fuse action takes 10 seconds, has an invariant condition of light, and an end effect of fuse fixed. The light match action has a duration of 15 seconds, start condition of have match, start effect, you no longer have the match and you have light, and then at the end, you no longer have the light. And that's, I think, the canonical example of the envelopes that Andres talked about. Find flashlight, kind of similar. The invariant condition is having light, and the effect is have flashlight at the end. And turn on flashlight. You need a flashlight at the beginning, and you have light at the end. So this is the problem we're going to be talking about. Now, if we find the causal landmarks for this problem, we're going to get fuse fixed, light, and have match. Okay? And that corresponds to the solution, right? We want to start light match, then we want to start fixed fuse, and then end light match. And this is the simple temporal network that describes the solution, right? And everything is great. Now, what happens if we change the duration of light match to 5 instead of 15? So this is no longer consistent, right? We can't use the solution anymore. But the causal landmarks do not change, right? Because the causal relaxation doesn't take durations into account at all. And so in order to address this, we define something that we call temporal landmarks, and they incorporate statements about what must happen and when it must happen. And as I will show you in a second, these allow us to discover more than just the causal landmarks. So we're going to define two types of landmarks. First is going to be fact landmark, and that says that fact F holds from exactly time point S until at least time point E. So first of all, these time points are symbolic time points, like in an STN, okay? So we don't have the exact time, but just the name for when F becomes true and when we no longer need F. And so this is, it's not a very important point, but it is, it makes a subtle difference, as I will explain later. And then the second type of landmark we define is an action landmark. And it's really a snap action or an event. So I want to say that event E, which is the start and end of an action, occurs at time point O. Okay, so a fact holds for a duration, because states have a duration, and snap actions are instantaneous. And then, of course, we can generalize this to disjunctions over facts and events. And in addition to these landmarks, we maintain a set of simple temporal constraints between these symbolic time points. All right. So I've defined two types of statements I can make, three if you count the simple temporal constraints. How do I discover them? So we're going to take an approach that's similar to backchaining and classical landmarks, and that basically says start with something that you know has to happen, which is the goal must be achieved. And then you want to draw some logical conclusions from that. So we define a set of derivation rules to do that. So what I'm going to do now is first I'm going to show you an example of how these derivation rules work, and then I'm going to kind of informally describe the rules. So this is going to be the example of the flashlight match seller with the 5-second duration for light match. Okay. So we're going to start with, we know that the goal must hold from some time point, which I'm going to call G, until the end, which I'm going to call E. And so I'm going to say that holds GE fuse fixed, right? And it's going to look like this, right? So we have holds fuse fixed from G to E. Now, the only event that can achieve fuse fixed is end fixed fuse, right? That's the only thing that has fuse fixed in its effects. And so that means that end fixed fuse has to happen at exactly time point G, right? And this is where I'm using the fact that fuse fixed becomes true exactly at G rather than at some point before G. Okay, so this allows me to kind of schedule this more accurately. And just note that this is just a notation, the end fixed fuse thing. It's not part of the STN I'm building here, okay? Or TPN really. Right. So I know that fixed fuse has ended, and therefore it must have started, okay? And so we have occurs starts fixed fuse at time point SFF with a temporal constraint saying that their separation is 10 because the duration of fixed fuse is 10. Now, the invariant condition of fixed fuse is having light. So because of the slightly weird PDDL 2.1 semantics, sorry Maria, so light has to hold from some point after the thing started until right before it ends. So I'm going to define two new time points. So it ends some epsilon before end fixed fuse. I would have liked to have something greater than 0, but I can't. So epsilon is the best I can do. And holds light starts from sometime before SFF until epsilon before G. Okay? Now, this is where it gets interesting. So we know that we need to achieve light, right? Because we have holds light. And we know that we need to achieve light for a duration of at least 10 minus epsilon. Now, there's two achievers to light, right? One is end turn on flashlight, and one is light match, start light match. But start light match is going to delete light after 5 seconds, right? That's again, the envelope thing. So we can't fit a 10 minus epsilon duration in a 5 duration envelope. And so we know that this occurrence of light has to be achieved by end turn on flashlight. Okay? Now, as before, if we end the turn on a flashlight, then we must have started it. And to turn on the flashlight, we must have it. So we must have flashlight. And the only possible achiever of have flashlight is end find flashlight. And therefore we must have had start find flashlight. And therefore we must have light throughout the duration of finding the flashlight. So this is for a duration of 2. And now I'm going to do another trick, and I'm going to look at the first time possible achievers of light match. Sorry, of light. And so, while again there are 2 achievers of light, only one of them can be used to achieve light for the first time, and that's start light match. And we can discover this in basically the same way that Llama does by building the relaxed planning graph without the achievers of light until it reaches a fixed point. And we discover that start light match is the only first time achiever, and so we start light match, and then we have end light match. And this is almost a complete solution to the problem. So it's not a fixed schedule, and it's missing, I think, a few temporal constraints, but it basically tells you everything you need to do. So I kind of cheated here a little bit, because I also should have used the first achiever rule on the first occurrence of holds light. So I would have discovered basically two landmarks that say that we must have a start light match, and their temporal constraints would have allowed them to overlap. But that's basically the idea. So just to review the 5 derivation rules we defined. So if a fact f must hold for a duration of d, then f must be achieved. And furthermore, it must be achieved by an action which does not delete f at the end if its duration is shorter than d. And f must be achieved for the first time. Also, every action must have a start and an end, and its invariant condition must hold between the start and the end. And these are kind of obvious. Every event must have its condition hold when it happens, and every event causes its effects to happen when it happens. So these are the derivation rules. Now, in fact, there was some previous work by Marzal, Onainda, and Sebastia that also did temporal landmarks. What they did was slightly different. They started with the causal landmarks, and then they used deadlines to refine 3 kind of temporal envelopes for each one. So necessity, validity, and generation, which kind of have a correspondence to our start and end of the fact landmarks, which you can read a bit more about in the paper. So the thing about their approach is that it only gives you more than the causal landmarks if you have a deadline in your problem. While this approach kind of infers implicit deadlines as you go, so it can infer more than the causal landmarks even if there are no explicit deadlines. But having said that, a lot of the reasoning, a lot of the derivation rules, and some of the propagators for these envelopes that they implemented and we haven't could actually be very useful for us as well. All right. So, great. I told you, hey, I can discover landmarks. And now the next question is, good, what are you going to do with them? So there's a few things we can do. First of all, we can use the landmarks as kind of a plan skeleton. And if you happen to have a planner that operates over state plans or TPNs or things that basically look like the landmarks that we discover, that's fairly useful. And we happen to have a planner like that. That's T. Burton, David Wang's planner, which he presented at AAAI last year. The other thing you can do is you can take the landmarks you discover, ignore everything you know about the actions and the facts, and just use the temporal constraints and the events to derive a heuristic on make span. So that's basically an SDN. Or you can take a look at the actions that have to happen, and you can estimate the cost that you have to incur, and maybe the cost represents risk or something, and you can get an estimate of how much risk you have to take until you find your goal. And finally, you can compile your landmarks into the problem. And that is what we did, at least for this paper. So we implemented a compilation that discovers the landmarks and writes a new PDDL domain and problem file with these landmarks compiled into the problem. Now, when you're compiling disjunctive landmarks, there's a bit of overhead, which comes from the way we did the compilation. So in our experiments, we basically limited the size of the disjunction to either 1, 4, or infinity. Right? So if the size of the disjunction is limited, we basically ignored all of the landmarks that have a disjunction bigger than the limits. So single landmarks are really the easiest to compile. They have very little overhead. So we took the benchmarks from IPC 2011 and 2014, discovered all the landmarks. And so we took 5 minutes to discover landmarks, and then we left 25 minutes for the planner. And we used POPF, TFD, and YASP from these IPCs, so just the IPC submissions. Now I'm going to show you the results on two types of domains. So first, the results on temporally expressive domains, and there's very few of these. I have to join Anders in that. So in fact, there's three: match seller, TMS, and turn and open. Now match seller, all the planners solve all the instances, so we can't really improve them, right? There's nowhere to go. In TMS, we had a very significant improvement, I think. So POP-F solves 6 more instances in both 2011 and 2014. And with the help of the Temporal Landmarks, TFD manages to solve 2 instances from 2011. With turn and open, the Temporal Landmarks don't really help. And the reason for that is that turn and open is a temporally expressive domain, but the required concurrency there is really not the interesting part of it, right? It's basically you need to turn the handle and then open the door, but then it's just a gripper with a combinatorial explosion. So the temporal landmarks are not going to help you there. Now, we also evaluated on the non-temporally expressive domains. There's a lot more of these, and here I'm just showing the domains where there was an actual difference between the different versions of the problem. So here we also have YASP. Of course, it's not going to solve anything with required concurrency. So although we don't do very well here, there are a few examples where we do improve. So in POP-F, if you use the big disjunctions, you can solve 5 more instances of parking. And in YASP, you can solve more instances of park printer if you use disjunctions of size 4. And there was one more which I am not finding now. So that just kind of shows that the disjunctions do help you, and our compilation is very inefficient with regard to the disjunctions. And so we believe that if we use the landmarks in a more integrated way with the planner, we can improve upon this even further. So to conclude, we know that landmarks work well in classical planning, in partially observable planning with sensing, and diverse planning, and over-subscription planning. And in fact, I think Antonin is going to present a paper about multi-agent planning with landmarks tomorrow. And also in temporal planning, at least for temporally expressive problems, hopefully more. And so I want to ask you, what else are landmarks good for? And also, I think that probably the influential paper award from 2013 was justified. Thanks.